Hello everybody, my name is Sebastian Böcker. I come from the Friedrich Schiller University Jena, and in this talk I'm going to talk CSI FingerID, and it's a behind the scenes talk. I'll say in a second what that means. Before I start, one warning: I'm a mathematician, I'm a bioinformatician, but I'm not a chemist, so I'm very sorry if I might get a few details wrong here and there. Another warning: I record this talk live, that is, I'm trying to do it more or less in one take, so I might get muddled here and there might be awkward silences. But I really hope that this makes the talk a little bit more lively. So, without further ado, let's start. So this talk is not about using our software. We have video tutorials that show you how to use our software, but this is not the talk. This is about, trying to explain how our scientific approaches work, why they work, why we did things this way and not another way, and also how well it works. So that's the topic of this talk for CSI FingerID. And this is, so to say, the full Monty of the different scientific approaches that we have developed for analyzing mass spectrometry data from small molecules. I already covered Sirius and Zodiac in the previous talk, so you're free to watch that, and it's also helpful to understand certain aspects of this talk. And in this talk, I'm going to talk about CSI FingerID. Now, it's important to notice again that this is about the scientific approaches and not the software. So software development is only the very last step. And our software now comes with shiny user interfaces. But for us, obviously, the more interesting, gratifying stuff is really to develop a scientific approach that can analyze such data. So before we start, what are we talking about? This is a very short slide telling you that. I made a much longer introduction in the talk about Sirius and Zodiac, so feel free to look at that. But just a few details. We are talking about small molecules. We're talking about small molecules of biological interest. That's metabolites, but it also includes drugs, illegal drugs, toxic compounds, stuff from food, and so on and so on. So everything we might expect to find in our samples. I will call these molecules biomolecules, or sometimes even metabolites. This is really just to make it short. I'm aware that some people have a problem with that, and they say, these are not biomolecules, what I'm interested in, but I don't want to get into this discussion. I just wanted to have a short word. Furthermore, we are talking about LC-MS data, so liquid chromatography mass spectrometry. But that's also not that important as long as you somehow have a way to separate your compounds. The interesting part is we are talking about tandem mass spectrometry, abbreviated MS-MS. Again, some people use different abbreviation to differentiate high mass accuracy data from low mass accuracy data. I'm not getting into that. I'm only talking about higher resolution data, or more precisely, high mass accuracy data. Because for us, in this application, high mass accuracy is the one thing that is important. High mass accuracy here means mass accuracy of 10 parts per million or better. The better your mass accuracy, the better it gets. The method also will still work for 20 ppm data, but 10 ppm is what we usually assume. If you have 2 ppm data, fantastic. Everything will be better, everything will be faster. You can add 5 percentage points to annotation rates and so on and so on. I'm talking about data-dependent acquisition, DDA, or more precisely, I assume that your compounds got separated, so every tandem mass spectrum only contains a single compound, or more precisely, billions of copies of the same compound, but not two compounds that have to be separated, as it is the case for DIA. And all of that, again, is what we can process out of the box. So our software Sirius can handle such data and give you this analysis results. If you need something different, something special, we also have other things available, like we are working on separating, say, chimeric spectra, but this is not implemented currently in Sirius, and you would have to contact us for that. Before we start to talk about what CSI FingerID is about, one warning: CSI FingerID, this talk, and in general these so-called in silico methods, they are not about lipid annotation. Lipids are different. And I mean the real lipids here. Some lipid classes are listed there as examples. And these lipid structures are really different because we usually also annotate them at a different level. We can generate them combinatorially. We don't know where double bonds are, and so on and so on. And that's the nice thing, lipid fragmentation is relatively easy to predict. So using CSI FingerID for that is not a good idea. We'll integrate something into Sirius that can also annotate lipids, but it won't be CSI FingerID. So we'll probably use one of the more dedicated approaches. In fact, there are many, just 3 examples given here. Use those if you're interested in lipid annotation, or wait until we integrate something into Sirius for that. By the way, we are still searching for a nice name for that, so if you have suggestions, please let us know. And another field that is somewhat related to small molecule annotation via tandem mass spectrometry is obviously shotgun proteomics. So there was always the hope that we could reuse methods from proteomics, shotgun proteomics, for peptide identification also in the field of small molecule research. After all, they have been searching structure databases for more than 25 years, and they are highly successful with doing so. But I don't think this is going to happen. And there are good reasons why this is not going to happen. And I have listed some of the differences between peptides and metabolites here. And there are many important things like this high structural similarity. We have macromolecules, peptides and proteins are at least on the level of mass spectrometry simply strings. But the other thing is similar to lipids. Fragmentation is relatively easy to predict, at least the ideal case, whereas for metabolites, even that is a super hard problem. And that's actually something I'm going to talk about in a few seconds. So I really don't see this is ever going to happen. Sorry about that. So what has been used in small molecule research to annotate spectra is spectral library searching. In fact, it has been used for many decades because it has been used for EI, electron ionization spectra, since at least 1969. I have already talked about the problems with that. You can basically only identify or annotate things where you have a reference available. A reference has been measured, so you can compare the spectra, and that is usually limited to stuff where commercial reference is available. So in many cases, spectral library search will simply tell you that, yeah, it's not in the spectral library, so it's something we have no idea what it is. So what do we do then? So we have these relatively small spectral libraries, and 10, 12 years ago they were even smaller. And we have these relatively large molecular structure databases. And they can really contain hundreds of millions of structures easily. So somebody asked the question, or the question comes into mind, wouldn't it be much more convenient to directly search in a structure database as they are doing it in shotgun proteomics? Is that possible? Now, as far as I know, the first ones who asked this question were Hilgrand and co-workers in 2008. And back then, they had a first approach for that. They used the commercial software. Yeah, it worked so and so well. But I think somehow this all started off the complete field of in silico methods. So we want to search in a molecular structure database, but what exactly do we mean? The thing is, stereoisomers often fragment very similar. So to a point that we can't really distinguish between them with a tandem mass spectrum. Some peaks might go up, other peaks might go down, and you might also find examples where they fragment not that similar, but in many cases they will be, at least for a general purpose method, indistinguishable. That doesn't mean this is not important. Obviously, the distinction between these two is important. It's just that an in silico method can't do that for you. Something like CSI FingerID. To this end, we consider structures on this level, which we sometimes call 2D molecular structure. You can also call it just molecular structure, constitution, bond structure, and so on and so on. So when you use CSI FingerID, this might be a search result, and then you have to decide which stereoisomer it actually is. But this won't be used in our evaluations simply because I don't think general purpose method will ever be able to do that. Maybe we can do something in the long run, but also not for all stereoisomers. We will see how good that works. Next question, where do we search? There are obviously different possibilities. And maybe the first one that comes into mind is, let's consider all chemically feasible structures. Now there's a nice paper from 2005 where they generated all possible molecular structures for a certain nominal mass, and they did that for all masses up to 150 Dalton. They only did that for these 4 elements, which are arguably the most important for biomolecules. And then, they provided the numbers in a table, and I took the liberty to plot that. Notice that here you have a log scale. So when you go one step up here, that means you have 10-fold more structures. And what you see is you can nicely fit a regression line through there. And this looks much like it's an exponential increase in the nominal mass. And if you just assume that it continues like that, you can make an estimate on the number of structures with mass up to 1000 Dalton, which is probably the interesting mass range. And then you see it's definitely more than 10 to the 80 structures with mass up to 1000 Dalton. And you might know that it's estimated that there are 10 to the 80 atoms in the observable universe. And this is only for these 4 elements. So if you add more elements into the soup, then you also get more structures. So I would say it's completely impossible to even consider that, at least when you're searching in a molecular structure database. So what are our options? As I said, all possible structures is not really an option. You couldn't even store that. You would need the whole universe and more to store this database. There are other databases, such as GDB17, which contains billions of structures, but unfortunately, it's not a public database. So I also think that it's too large to search there successfully. What is a decent database to search in is PubChem, or alternatively ChemSpider. It's really hard. Whereas we also have more dedicated databases where only biomolecular structures are stored, such as HNDB or CHEBI, and so on and so on. And if you add all of them together, you end up with a database which contains less than 1 million structures currently. I mean, they are growing. Alternatives would be you use an in-house structure database, and you can also generate such structure databases with hypothetical structures. There are examples like Biotransformer or the MINE databases, which transform existing structures into new structures using in silico transformations, in silico enzymatic reactions. You can also generate them combinatorially, and so on and so on. And the point is, I will always show you results in evaluation searching in PubChem. That is not because it makes a lot of sense to search there in practice. That is because PubChem is really hard. It's not too hard, so you can successfully search there, and you will see that often the correct answer is actually annotated. But in many cases you won't find it, and that's simply because it's so large and contains so many molecular structures which are definitely not of interest for us, that we are probably, we are interested in biomolecules. Remember, that also includes molecules of biological interest. So in application, it makes sense to search in one of those databases, but in evaluation, we'll search here. This is hard, but it's not too hard. So we'll see that some methods perform well there and others will have, will struggle. And once again, the slide that explains why we are searching in a database in evaluations when it's actually harder than what we want to do in practice. And this is again the where is Wally example. Okay, can you spot Wally? Wally is the guy depicted here and here, but you have to spot him in here. And that's pretty tough, okay? On the other hand, what about this example? Can you spot Wally somewhere in this picture? Now, obviously, that is much easier. And that's more or less the difference, searching in PubChem versus searching in a small biomolecule database. And the problem is, if you evaluate on this side, then it might be too easy. It might be, every method can spot Wally there, but that doesn't mean anything. So you'll get inflated numbers. All methods will more or less look the same because the answers are easy. I mean, the big biomolecule database is still big enough, but a small biomolecule database, that might be just something random happening. So you should always look out that people are actually evaluating their methods also searching in PubChem. So let's talk about in silico methods. What is that? I already mentioned this several times, and in silico method simply an accepted term for searching with a tandem mass spectrum of a small molecule in a structure database. There are 3 paradigms for it, and if you are precisely speaking, then this in silico only applies to the first paradigm. So the first paradigm tries to transform a structure into a mass spectrum. That's more or less what you do when you also simulate or generate an in silico spectrum for a lipid or a peptide. And it's not easy. So there are quantum chemistry methods and there's machine learning for that. And I'll talk about that. The second is the simplest, conceptually simplest, which tries to explain a mass spectrum for any given structure. And then you try to find the best explanation. And the third paradigm, that is actually where CSI FingerID belongs. There you take the mass spectrum and you try to transform the mass spectrum into structure information about the structure, and you only use the structure information to search in a structure database. Now, the first paradigm has the advantage that you have to do this transformation from structure to mass spectrum only once. You can then store those mass spectra, and then if you really search with your query spectrum, you only have to do library searching. So that's very fast. So the simulation is time intense, but after that, you only have to do the same, invest the same time that you would do for a regular spectral library search. The last paradigm has the advantage that as soon as you have transformed the mass spectrum into a structure, you can do all the comparisons on the structure level, and that is again very fast. The second paradigm does not have these advantages, so it's relatively time intense. The advantage here is that it's by far the easiest to explain and to understand what it's actually doing. But these are the current paradigms. There might be new paradigms tomorrow. I don't know, maybe somebody comes up with a new idea. So for the first paradigm, if you want to use machine learning, there's currently one method, and that is competitive fragmentation modeling. Felicity Allen came up with this method in 2015. Since then, there have been only minor changes. Certain parts of the machine learning were replaced, and this is really groundbreaking research. It's a very sophisticated combination of different techniques, both from machine learning and from statistics. And I'm positive that I can explain that to you, but it would take very, very long. I mean, it's not that I can explain it to you, but that I can actually explain it, because it's not that easy. It's really sophisticated. So if you want to know the details about it, I can only point you to the paper. And so you have to look there for yourself. The other possibility for the paradigm structure to spectrum is quantum chemistry, ab initio simulation of small molecule tandem mass spectra, or let's say fragmentation spectra. There have been several papers about it, in particular by Stefan Grimme. Let's first look at the spectra. You see that the spectra that come out of this simulation, they are similar. Yeah, there's similarity, but it's not that they are perfect in a way. The other point is they are small, and that's for a reason, because this is electron ionization. And it seems to be much harder to simulate spectra for tandem mass spectrometry. At least this is what I got from the literature that I read about it. Even bigger problem is probably running times, which is easily thousands of CPU hours to simulate a single spectrum. There are different versions now of how you can do the simulation. And for the simple simulation, that's 100 CPU hours, but then unfortunately, the more complicated it gets, the more accurate it gets, the higher you have to invest in CPU hours. Now, if we do some simple calculations, if we really want to simulate all spectra for a database containing 100 million compounds, then you end up with 10 trillion CPU hours, and that would be on a cluster with 10,000 CPUs. That would still be 11,000 years. Obviously, you don't have to do that for all of PubChem, so you might just do it for a smaller part, but it will nevertheless be extremely time intense. And that's only EI spectra, and that's only very small compounds. I mean, this obviously the running times increase if your molecules gets larger, say up to 500 Dalton. There is a possibility that everything will get better with quantum computing. Let's see how they make progress in the next 10, 20, 30 years. But yeah, we will have to wait that quantum computing becomes really broadly available so that we can test it and then run such a computer for, again, maybe hundreds or thousands of hours to simulate such spectra. I'm very interested how this goes on. I said that the conceptually simplest to understand is combinatorial fragmentation, the second paradigm where you have both the structure and the spectrum available, and you try to somehow fit the structure into the spectrum. How well do they agree? And with that we mean how many peaks, how much total peak intensity can we explain from the spectrum with this structure? And we do that with every candidate, okay? And that's the time-intense part. And what we do is we don't simulate really in silico fragmentation. Instead, we simply do a combinatorial breaking of this spectrum, of this molecular graph. And then we see if we can explain peaks with these fragments that we generated from here. Even breaking a molecular graph is a nasty problem. So we have to make simplifications there. We have to use heuristics so it actually runs relatively fast. And still, the running times will be higher than for the other two approaches. That's unavoidable here. The first such combinatorial fragmentation approach was in 2010, MedFrag, from the group of Steffen Neumann. And since then, there has been Magma, which made things faster, and then have been numerous other methods, but they didn't really add new ideas to this combinatorial fragmentation idea. And now finally, we come to the last paradigm, which is mass spectrum to structure. But before I talk about CSI FingerID, I want to talk about its predecessor, which is FingerID. And that is work by Markus Heinonen, who was back then a PhD student with Juho Russo. And what do I mean with molecular structure information? The important point to notice here first is that what I'm going to talk about now has nothing to do with mass spectrometry. This is only about structures, molecular structures. Molecular fingerprints are a way to deal with molecular structures. And one thing you can do with them is virtual screening, and there you have to decide if two molecular structures are similar or not. And that's a non-trivial problem. There are ways how to do that from a graph theory perspective, but that's also nasty problems such as the maximum induced common subgraph. We're not talking about that. But initially, these molecular fingerprints were, as far as I know, first used by Morgan, the Morgan fingerprints in 1965. And they were back then used to check whether a structure which you wanted to add to a structure database was already contained in the structure database. Okay? Again, no mass spectrometry connection whatsoever. And then they have been used for at least 2 decades in virtual screening. And there you want to, as I said, decide if two molecular structures are similar. And how do you do that? What you do is you transform your molecular structure into a binary fingerprint. In our case, this binary fingerprint always has a fixed length. There are different types like MAX and PubChem. Actually, the Morgan fingerprints are a little bit different. They are combinatorial fingerprints, but let's focus on these that have a fixed length. And there you have a list for each type, a separate list, which now tells you what does each position in this bit string mean. Yeah? For example, this position encodes for this substructure, and this position encodes for this substructure. Actually, this example has nothing to do with these two structures here, so don't try to find a connection there. Anyways, you go through your molecular structure, and then you check, does it have this substructure? Yes, so you put a 1 here. Does it have this substructure? No, so you put a 0 here. You do that for all the substructures in your list, okay, which has a fixed length. That's the number of bits in the molecular fingerprint. Each of these positions will be called a molecular property, which a certain structure can have or not have. Doesn't matter how often it has the substructure, it's just important if it has it at least once, in which case you put a 1 there. And then for some of these bits inside such a molecular fingerprint, for some of these molecular properties, you can really tell what they are. For example, the presence or absence of a hydroxy group attached to a carbon, to be precise. And actually, you can have a look at these lists, and you'll find these lists that describe these properties, molecular properties, which are part of a particular molecular fingerprint, in this case, the PubChem cactus molecular fingerprint, and you can look through them and see what each bit describes. For some of them, they have given descriptions, but that's only for the first, 50 or 100 or so. The rest doesn't have a description, but they're encoded by these smart strings. Now, a smart string is like a regular pattern, but for structures, it's similar to a SMILES. I'm not going to talk about that. It's not really easy, and I'll come back to that. That's why in CSI FingerID, we do not only show you the smarts in the end, but also, maybe easier to grasp visual representation of that. Okay, good. So far, no mass spectrometry. Now let's get back to mass spectrometry. And the question there is, can you predict the molecular fingerprint? So all of the molecular properties of an unknown compound from the tandem MS data. So you have a query, you have measured the tandem MS, and you want to predict the molecular fingerprint. Yeah, all of the molecular properties 0 or 1. Is it present or is it absent? This is a very cool question to ask. It's actually older than FingerID, and I'll come back to that. I will show you an example of a method that tried to do exactly that a long time before FingerID. But FingerID also tries to solve this. How do you do that? Now, what we could use to predict such a molecular property, remember 1 bit of the fingerprint, we could try that using a voodoo chicken. A voodoo chicken looks at the query MS, and then it decides, does the molecule that produced this spectrum contain a carboxyl group, yes or no? Okay, and if the answer is yes, it picks on the yes button, and if it's no, it will do it here. Now, a lot of people have asked me, why do I mention a voodoo chicken here? What is that? Don't Google voodoo chickens. I think there are several upsetting photos and videos available which have nothing to do with what I have in mind. If you don't like the voodoo chicken, then instead you may consider other ways of predicting such things. Maybe Paul the Octopus to predict outcomes of soccer games, or you can think of the Oracle of Delphi. You can think of Phil the Groundhog, or you can think of a Palantir. I don't mind. The thing is, voodoo chickens are easy to store. And that allows us to predict a complete fingerprint. Remember, a fingerprint consists of many, many molecular properties. And for each of these molecular properties, we now use an individually trained voodoo chicken. So in full, we have a battery of voodoo chickens for that. Now, obviously, that's not really a good idea. Voodoo chickens are not that easy to get. And I don't know if you can order them at Amazon. And probably this is also not okay with animal welfare. So we had to search for an alternative. So what can we use instead of voodoo chicken? Machine learning. Now, this is a visualization of machine learning, and unfortunately, it's all wrong. This is definitely not what machine learning looks like. This is similar to the idea, to the spirit of so-called expert systems, which is a computer learns from a human, from human expertise. And this idea was mostly abandoned in the 1990s. And it's not what today's machine learning looks like. Now, the previous slide was very beautiful, and this slide is probably not as beautiful, but this is much closer to what machine learning really does. Because you have to understand that machine learning is math plus math plus math. Or in detail, machine learning is linear algebra plus statistics plus optimization. So how does that work? You have two classes that you want to separate, a positive class and a negative class, doesn't matter. And you have features, for example, the height and the weight of these things, of these dogs and cats that we want to separate. And now we want to find such a curved line here that somehow separates the cats from the dogs. Now the nice thing, or what makes support vector machines very nice, is they now embed this into a very high dimensional space such that you get a linear separation between the cats and the dogs. This is again shown as if it was 2D, but this is now, I don't know, 1000 dimensional, or it can be even infinite dimensional. And in 2 dimensions, this is a line, and in arbitrary dimensions, this is a hyperplane separating those two. And support vector machines are maximum margin classifiers. That is, you choose this hyperplane in such a way that the minimum distance to the dogs and the cats is maximized. The minimum distance is maximized, okay? In 2 dimensions, that is then defined by 3 points. 2 points give you the line, 3 points tell you a line with maximum margin. The last step of FingerID, how can we now use this predicted fingerprint to search in a molecular structure database? That is relatively easy, and we don't even need mass spectrometry for that anymore. I told you in the beginning that as soon as we have transformed the information into structure information, we can forget about mass spectrometry. This is now something they also do similarly for other tasks. Like, it's similar to this virtual screening approaches. So we have a list of candidates. We get them from the database, we get them by mass, exact mass, precursor mass, or we get them by the molecular formula, which we have computed using Sirius. Now, for each candidate structure, we know its molecular fingerprint. This is deterministic. I told you that this is actually how you can transform it. You look into each structure. Does it contain a certain substructure, yes or no? And then you put there 0 or 1. There are many software packages out there which can do that for you. Now, for each candidate, you now compare the fingerprint of this candidate structure with a predicted fingerprint. And we assume that we have done a good job predicting this fingerprint. Otherwise, why did we try it all? So our magic chicken are doing a good job here. So they are not doing a perfect job, so every now and then they'll actually fail. But assuming that this is the correct molecular structure, then they must have failed here, here, and here, and here. So 4 of these voodoo chickens have failed. Now, parsimony tells us that if it's really correct that our fingerprint is a predicted fingerprint is very close to the true fingerprint, then we can rank all those structures by the number of mispredictions that our voodoo chickens did. So the candidate with the fewest numbers of mispredictions is our first rank of our output list, and then we go down and down and down with more and more errors that we presumably made if this candidate, this structure was the correct interpretation. And then in the end, we can check how often we got the correct answer on the first position, and so on and so on. This is now the complete FingerID workflow. I already told you many of the details. One cool thing, I mean, you don't have the voodoo chickens here, you have the support vector machines. And one cool thing about support vector machines is usually for machine learning, you somehow have to encode now the information that you want to get into that, which is now here a mass spectrum. And how do you encode that? That's not easy. You can encode each position, like is there a peak at 141 Dalton? But there might be something different, many peaks at 141 Dalton. We are using high mass accuracy data here. The cool thing is that we don't have to encode that for support vector machines. It's enough if we can somehow compute the similarity between different mass spectra, and that's very similar to the dot product. I'll come back to that in a second. For the moment, the workflow goes now to the predicted fingerprint. We then compare that to all the candidates, and actually in the original FingerID paper, they used a weighting which was not so good. Without the weighting, it actually worked better. But yeah, we don't have to go into the details of that here. And hooray, we have finally reached FingerID. What I'm going to tell you now started off at the GCB 2013 in Jena. Precisely, it started off during a bus ride from one part of the conference to another. Juho Russo approached me. I think Kai and Hui Bin were also on the bus. And he said, I like what you are doing. And I said, I like what you are doing. And we thought, maybe we can join forces. Maybe we can make things better if we somehow get this together. These two ideas, we were more on the combinatorial side. They were on the machine learning side. So maybe we can make better identifications if, we somehow merged that. It was, more or less a wild idea. We didn't know if that would work. That's, I think, how science usually works. Now, what is the new ingredient compared to FingerID? If you have listened to the previous talk, I told you about fragmentation trees. I'm not going to talk you through all the details again. I mean, the fragmentation tree somehow explains the tandem mass spectrum and so on and so on. But here the important point is, when you compute a fragmentation tree, there are no structures, no spectral libraries, no structure databases. This is really taking a tandem mass spectrum and it's transferring it into a fragmentation tree. So far, we have used that only to find the molecular formula of the compound. But can we also use that to derive information about the structure? And indeed, the point is, yes, we can. Remember the voodoo chicken. The voodoo chicken so far saw an input MS-MS spectrum and it tried to predict, does it contain a particular subgroup? one molecular property. But now Sirius can also compute a fragmentation tree. So what the Voodoo chicken now sees is not only the spectrum, but also the fragmentation tree. Can this help the Voodoo chicken to decide whether or not the carboxyl group is part of the query molecule, the unknown structure? To understand why it might be a good idea to combine machine learning and combinatorial optimization, I have to tell you that machine learning is not particularly good at solving combinatorial puzzles. Here are two examples of such combinatorial puzzles. They are from Simon Tatham's puzzle collection. It's a really wonderful collection of single-player puzzles where you can generate an arbitrary infinite number. It's not infinite. I'll come back to that in a second, of such puzzles, and then you have to tell the machine like where to put what. This is, I think, called towers, where you have to put towers of different height onto this so-called Latin square. By the way, Latin square because each number here appears only once in each column and each row, columns and rows. This is called signpost, I think. It's a little bit different. The clues that you get are different, but you have to find out what number goes where. Now, as I said, machine learning, I don't believe you have any chance to solve that with machine learning. You could generate arbitrary amounts of training data, but nevertheless, I think no machine learning system could really solve that for you. Whereas for combinatorial optimization, this is a finger exercise. And I mean that in two different ways. One way is, I think I could give that as an exercise to undergraduate computer science student, bioinformatics students, and they have to write me a software that solves these things. And I think after a few weeks, they'll have found a nice software which could solve these much more efficiently than any human could do, okay? But it's even more dramatic. When you hit the new button inside this app, Simon Tatham's puzzles, a new such Latin square is generated. Then clues are generated. These are, for example, in this case, numbers here which tell you how many towers you can see. And then what it does, in the moment you press the button, it also solves this thing. That is, assumes it knows nothing, only these clues, and tries to fill in the Latin square just from the clues. And it does that at a specified difficulty level. You tell it, do you want an easy one? Do you want a hard one? Do you want a mind-boggling one? And then it tries to find out if it can be solved at this difficulty level, but not at an easier level. So you always get, if you want hard puzzles, you always get hard puzzles, never by incident one which is easy, okay? And if it's solvable at a difficulty level below the difficulty level you have specified, or if it's not solvable at the level you have specified, this is discarded, a new one is generated, and it's all starting from scratch, which might happen several times. But the point is, you press the button, you won't notice it. In the blink of an eye, the puzzle is there for you to solve, because this all runs in a, I don't know, few milliseconds, maybe 100 milliseconds at most, and then it's done. For combinatorial optimization, this is easy. Now, how can we use such combinatorial methods to improve our machine learning results? For that, we come back to FingerID. I have very briefly mentioned kernel-based learning, and I want to go into a little bit more detail so you can understand that. The nice thing about support vector machines and other kernel-based learning methods is that you don't have to explicitly define features. What's a feature? It might be the presence of a certain peak in our mass spectrum. It might be the presence of a certain loss. Our problem is that we don't know all important peak masses and all important losses, so we could encode everything, but then, we have too many features. It gets problematic on a different level. So for kernel-based learning, the cool thing is we don't have to do that. What we have to do instead is we define kind of a similarity function between tandem mass spectra. And you can think of the similarity function simply as the dot product. Actually, FingerID uses two such similarity functions. One is the dot product and one is the mirror dot product. Our mass spectra now can have different precursor mass, and so we also mirror both of them and then compute the dot product. And what we do now in the training phase is we use our training data, which is shown here, and we compute the similarity between any pair of these training data mass spectra, where we know what the correct answer is. Yeah, we know if we should put a 1 or a 0 there for a particular property, molecular property. Okay, but let's forget about that. That's just the output of the support vector machine, but we see the similarity here, and we now use that inside the support vector machine, but we don't have to explicitly define the features for that. Some mathematical things happen, then it's trained, and if we now have a query spectrum, we also transform that into such a vector of similarities. Again, these are all the training tandem mass spectra, so we compare our input tandem mass spectrum to all the training tandem mass spectra, and again compute these similarities, these kernel values, and we feed that into the support vector machine, and then it tells us, yes, it has this molecular property, or no, it doesn't. And how can we use a similar idea now that we have fragmentation trees? The nice thing is we can now use combinatorics to come up with different kernels, and this is just one of the examples that we came up with very shortly. And what it does is it is the common path counting kernel. It compares the two fragmentation trees, okay, two different training examples, or one is the query and the other is the training example. And it counts how many common paths does it find. Okay, these are losses inside the fragmentation trees, you might remember that. And this is, for example, an H2O loss. Okay, the other ones I don't have here. I don't know what losses these are, but if it has different colors, these are different losses. And now we count how many paths of these fragmentation, let's call it fragmentation cascades, are contained both in this tree and in this tree. And this is the result. Both of these fragmentation trees contain a path of losses, which is just this yellow edge. Both contain this H2O loss, both contain the red one, and then both also contain this path of length 2, where you first lose an H2O and then you lose whatever this yellow encodes. So the answer of the similarity calculation would be 4. And the nice thing is this computation can be carried out extremely efficiently. That's very, very easy, very fast. Now I told you that encoding the fragmentation spectra as fragmentation trees allows us to come up with different such kernel functions, different similarities. And in fact, we came up with, I don't know, 40, 50, 60 different such similarity functions. And these are just the ones that we currently use. They are all described in the Sirius 4 publication. And now you might think, okay, now we choose the best one from this list. But this is the cool thing about kernel learning. You don't have to. Instead, what you do is you stack them. Mathematically, that means you simply add them on top of each other, okay? And if you add kernels, you again get a kernel and you can feed that into a support vector machine. And why would you do that? Because sometimes a kernel might do crazy things. It might assume that two mass spectra or the corresponding fragmentation trees are similar, but they are not really. It's just a coincidence, okay? This happens every now and then. But if you add up all of these kernels, statistics comes in, and hopefully such errors cancel out. And this might sound a little bit theoretical, but in fact it's not, and we can actually prove that. This is now a slide from the PhD thesis of Kai Dürkop, which is a very good read. It won 2 prizes, and not everything from the thesis is published, so it's definitely worth to look into that and see what of the things we have done are so far not published. And here you see all the individual kernels. Back then it was different kernels from the ones that I showed you in the previous slide. And on the right, you see the multiple kernel learning where we have stacked those. We also added some weights. You multiply each kernel by a certain weight that doesn't give you much performance, but you get a slight advantage, okay? And what you see now here is the performance, the average performance of predictions when you use a certain kernel. It's measured as F1. I'm not going into the detail, but the higher the bar, the better the predictions are. Yeah? And here you see the PPK kernel, which is the FingerID kernel. And actually, this is the other FingerID kernel, how well they perform. And you see that, yeah, most kernels don't really perform much better than the PPK kernel, for example. Yeah, there are a few which perform better, but not that much better. But if you stack all of them, you suddenly get a better performance because errors canceled out. And suddenly your predictions become, yeah, much better. But not only much better, they also become more robust. And what do I mean with this? Here in green, the bar tells you how good, on average, our kernels performed. Yeah, the different kernels performed in cross-validation. I'm going to talk about that in a second, but it is simply on the training data itself. But unfortunately, the structures in the training data are often very similar to each other. So even though cross-validation makes sure you never evaluate something on the data you trained it on, it's nevertheless often too easy. So you should always also evaluate it on independent data. So a completely different data set measured by different people, different compounds, and so on and so on. And you see here in red, here you see how good, say, the PPK kernel performed on the independent data. And there's a rather substantial drop in performance, okay? And it gets even worse if you go to independent data, which is far, far away from your training data. Yeah? Then the performance drops even further. And that's the same again for all the kernels. But multiple kernel learning, you see that the drops are again, quite substantial, but nevertheless, even here, for the independent data, which is far, far away from the training data, it still gets a pretty good performance. And that's why CSI FingerID is so strong. That's the most important ingredient that differentiates CSI FingerID from FingerID. But there are two more ingredients. And the second ingredient is that we made our voodoo chickens smarter. You remember the voodoo chickens, which transform or predict from a query spectrum and the corresponding fragmentation tree whether or not a particular molecular property is present or absent. But now we allow the chickens to also tell us how sure they are. So they don't pick yes or no. They tell us it's rather probably absent, or I'm totally sure that it's present. They can now give us a number between 0 and 1. And on the machine learning side, this is the posterior probability of the molecular property that we are predicting it. And we use a Platt estimate to predict that. Now, since the words Platt estimate of the posterior probability is too long, we often use something shorter like Platt probability or just Platt estimate or just everything. That's all the same, okay? One is the technique we use to compute that, and the other is actually what we want to compute, the posterior probability. And you can actually see our predictions in the user interface of Sirius. This wraps CSI FingerID, so it's part of Sirius, the graphical user interface there. And here you see for some input spectra what the predictors did. And you see two things here. I mean, you see several things here. You see what is the actual molecular property that we are predicting here. You see the Platt posterior probability, the Platt estimate of the posterior probability. But what we also tell you is how well this particular predictor, this property, was predicted in cross-validation. So the higher this number, this is the quality estimate, it might now be no longer F1, but MCC, Matthews correlation coefficient, but they both measure the quality that we achieved in cross-validation. The closer this is to 1, the higher was the power of this predictor in the cross-validation. Okay? Now a predictor which is not performing very well in cross-validation can nevertheless be very, very sure, and that's just the math behind it. There's nothing around it, but it's doing a good job. So if it's very sure that this is true. It might be true, and we can't really do something about that in our automated classification, but you can now individually look at these things and decide for yourself whether or not you believe it. So you can be a little bit, more cautious for this particular molecular property. Now, Kai has added a graphical representation of the smart string, because as I said, the smart string are not easy to read for somebody who is not used to them. So it shows you a few examples of structures that contain this particular smart string and even highlights that. And it's not perfect doing that. It's really just for you to get an impression what this is about, so you can look at it. Now, one thing that you have to understand when you look at these molecular properties, even if we predict a molecular property, a particular molecular property to have a posterior probability of 0.01, that is, we are almost certain that it's absent from your query structure. This does not really mean it's definitely absent. And this is even if all of our predictions were perfect. Okay, if they were super accurate, which they are not, because we have trained them on training data and we somehow try now to predict something for data which we have never seen before. So it must be a little bit inaccurate. But even if it was absolutely accurate, okay, the point is the chances that you win the lottery are tiny, but the chances that someone wins the lottery is pretty high. And so we have loads and loads and loads of different molecular properties, and many of them are now predicted with very small posterior probability. And if there are hundreds of them with posterior probability 0.01, then each of them has a very small chance to be present in your structure. But a few of them will definitely be present in your structure simply because there are so many. Okay, that's just a word of warning. Don't be absolutely sure just because CSI told you this property, no, that's not in there, so I'm 100% sure that it's not in there. No, it doesn't work this way. That's not how statistics work. I'm sorry. Now, how can we use these posterior probability estimates to make a better scoring? Because that's our last ingredient. And the thing is, so far, we assumed that our predicted fingerprint was ones and zeros. But now we have this wonderful posterior probability estimates. And what we can do is, we can simply compute the posterior probability of the complete candidate, assuming independence, which, by the way, is wrong. And so we must be careful in the next slide when we interpret what comes out of that. So how is that done? We simply look at the query fingerprint, which is now a probability that this property is present or not. So 80% sure that it's present. And the candidate says it must be present. So these cases taken together have a probability of 0.8. So we look at the next molecular property, which is absent. And we also predicted it's absent, but with 20%. So how sure are we that it's absent? We are 80% sure that it's absent. So we multiply it with 0.8, 1 minus 0.2. So the next one is presumed to be present again. So we simply take this probability, in which case this is very bad, obviously. And the next one is absent in the candidate. So we multiply it again with 1 minus 0.7, which is 0.3. And this is now the total posterior probability, very simplified, of the candidate. Let's say it's the score of the candidate. But since these are all numbers below 1, and there are many, many of them, hundreds or thousands of them, you will get a tiny, tiny number, something 0.0000, so and so on. So what we do not report this number, we instead report the logarithm. And I'll show you in the next slide what that means. So now this is again the user interface of CSI FingerID in Sirius. And what you see here is different candidates that were now scored, and you see which score they got. And if you ever wondered why this is now always a number, negative number, and yeah, different negative numbers like there. The highest negative number is the top score. This is because this is now the logarithm of this posterior probability estimate. Okay, and you might now think, wow, this score difference, let's say these two have score difference 3. What does that mean? Now, if all of our computations were correct, that would already mean that the first candidate is 1,000 times more likely than the runner-up. So it doesn't really matter what the number here is and what the number here is, but the difference tells you how much more likely this guy is. Yeah? If you look at it's not like that, I have to tell you. It's not like that. It won't really mean it's 1,000 times more likely because we made so many assumptions in there which are wrong. Yeah? But it gives you an idea that a score difference of 3 already means something. And here we have a score difference of, wow, 25. That's a lot. Yeah? So let's look at the probabilities. And they are astonishingly small. For example, this score corresponds to this probability. And now you know why we don't report the probabilities. Okay? And the other score corresponds to this probability. And it's really the different numbers of zeros, yeah, after the dot that makes the difference here, not so much the numbers in the end. Yeah? And this is obviously two very different posterior probabilities, but as I said, since we made so many assumptions, they are probably not correct and you shouldn't treat them as such. But nevertheless, this is a huge difference between these two things. I would like to mention one more thing, and that is also in this nice graphical representation, we tell you something about all the molecular substructures in there, all the molecular properties. Those are the dots. The blue ones are molecular properties which are present in this candidate and which we also predicted to be present from the tandem mass spectrum. The bigger the dot is, the better the molecular property predictor performed in cross-validation. And the bluer the dot is, the higher the posterior probability. Yeah? And the same one is true for the red ones, and it's just the other way around. Yeah? Hopefully you find, for the correct interpretation, few red dots, and they are very small. That would be perfect, and not very red. That's the best that can happen. Now, there was another scoring which was already presented in the PNAS publication, so the original CSI FingerID publication, and we called that modified PLAT. Now, the positive things about the scorings are it performs consistently better than the original PLAT scoring. Okay? On independent data, on every data we ever evaluated with, it always performs better. But what is not so nice is we have no idea why. Yeah? There's no mathematical foundation or justification for the score. It was simply, yeah, try and error. In the end, we came up with this score. It works better. Hooray. Unfortunately, since we do not know why it works, we also do not know how to improve it. But we would like to improve it. So if somebody could tell us why the score is performing better than the original PLAT scoring, we would be very happy if you could share that information with us. Then we can try to further improve that. What we did instead was we came up with a completely new scoring. And this scoring is now considering something that we ignored in the PLAT scoring, and that's one of the reasons why these probabilities are not really accurate, and also not the differences, or the differences between the logarithm are not accurate. And that is that the molecular properties are not independent. If you look into these lists, you will sometimes find something like this. One molecular property encodes this substructure, and one molecular property encodes this substructure. But if a structure has this as a substructure, it will always have this as a substructure as well. So if you find this and predict this and you are correct, then you're no longer surprised that this is also in there, and you shouldn't treat it as if it was a total surprise that this substructure is also in there. And how can you model that? These things are no longer independent. We modeled it via Bayesian network, actually a very simple Bayesian network, a tree. I'm not going into the details here, but instead of multiplying just the probabilities from the PLET scoring, which are depicted here, it now uses these conditional probabilities. So I already know something about a certain molecular property, and then I'm no longer surprised to see another molecular properties. I mean, the magic then is estimating those conditional probabilities, or equivalently the joint probabilities. That was not very easy, but this scoring now performs better than the modified PLET scoring. And it's now also available in Sirius. With Sirius, I think 4.5, it now finally became available. It's much more complicated to implement it, so it really took us some time to get it to the user. If you want to know the details, as I said, it's rather complicated. There's a conference publication about that. And with that, we have everything we need to understand CSI FingerID. At least, from a high perspective, it's now enough. So we have fragmentation spectra, we transform them into fragmentation trees, we use multiple kernel learning. From that, we predict, or we first train this battery of support vector machines to replace our voodoo chicken. And if we have an unknown compound, the tandem mass spectrum is again transformed into a fragmentation tree. We don't need any databases or anything else to do that. We then feed that into the multiple kernel learning. We compare this fragmentation spectrum and this fragmentation tree to all of the fragmentation spectra and fragmentation trees from our training set. So now we can predict, is it on one side or the other side of this hyperplane of the support vector machine. And in the end, we estimate PLET probabilities. So PLET estimates of posterior probabilities, as I said, a little bit imprecise. And there are several papers, if you want to know more details, that describe this now. The initial idea of the multiple kernel learning, of using fragmentation trees to compute similarity kernels for these fragmentation spectra, is described here. The next publication is the last one, which describes the current standing, which kernels are actually used at this point of time. But the most important publication is then probably the PNAS publication, which contains a lot of the stuff that I'm presenting here. Now, one question which we are asked every now and then is, why is CSI FingerID using linear support vector machines? There are newer methods, cooler methods. There has been a machine learning hype, and support vector machines are so 1990s. Why are we still using them? Now, for somebody in machine learning, when you are using machine learning, you are pouring data at the machine learning, and then you are seeing how well it works. You might pour a little around with your data and try to improve something. But for somebody from machine learning, it's the other way around. They have the data fixed, and they try to change their linear algebra so that predictions improve. They steer their linear algebra until it works a little bit better. But this is not always the best way how to get a machine learning system which is then very robust. And what we noticed that for predicting molecular properties, it's really important that you stay simple, and linear support vector machine, linear classifier is the simplest, and it's also working very robust. It's generalizing very well to new data, which it has never seen before. And this is in the end what we want to do. We want to predict the fingerprint of a compound which the system has never ever seen before. For example, random forests. This is also not a very new method, but random forests are known to work very well if you evaluate them and cross-validation on the training data. I'll come to that in a second. But then they generalize rather poorly if you give them completely new data, which is totally different from anything the random forest has seen before. And you have to be careful that you don't overfit, that you don't make your machine learning method look better in evaluation than it does in practice. One example, and that's one of these examples that people have in mind there, is that these deep neural networks become very prominent, very well known, because they could solve Go. Suddenly you could play Go better, a computer could play Go better than a human. But the point is, the programs, AlphaGo, AlphaZero, that do that do not only use machine learning. They actually also use combinatorial optimization, minimax optimization, and alpha-beta pruning, or the stochastic counterparts of these techniques. So if machine learning had been around or DNNs had been around for, I don't know, 50 years or something, and somebody would have invented now these combinatorial optimization methods, everybody would say, oh, this minimax optimization has solved AlphaGo. But it's not true. It's a combination of these two things that perform so well, because these games also have something combinatorial, and that's something that DNNs don't like that much. And in that respect, why do I think that the mass spectrometry data from a small molecule has combinatorial things in it? Because you can have a peak at 120.1 something Dalton, and it means something completely different from a peak which is, I don't know, 5 ppm away from that, because it stems from two different fragments with two different molecular formulas. But for machine learning methods, these two peaks are mostly the same. It might be the same peak with a little bit more mass inaccuracy. That's totally possible. Machine learning is not stupid. As long as you now in your training data have examples that show that it might mean this substructure or this substructure, it will pick that up. It will learn that. But what about those cases where we don't have any training examples? And again, this is where we want to go, to novel compounds, which we cannot find by spectral library search. And I already mentioned that in the very beginning. Neural networks are also not such a novel idea. They have been around for many, many years. In the 1980s, neural networks were the totally cool stuff. And then in the 1990s, people turned away and went to support vector machines. So these so-called experts in the 1990s would have probably told you, why are you using neural networks to predict a molecular fingerprint? That doesn't make sense. Use some cool machine learning, something gold, something Gucci to predict that, and not these neural networks. Everybody knows that they are not working very well. And in this 1990 publication, they actually did that. They used neural networks to predict these fingerprints, molecular fingerprints. But that didn't work so well, because you now have to, for example, encode the features that you find in such a mass spectrum in a way such that a neural network can work with that. And the support vector machines of FingerID did the job much better than this neural network. Okay? So it's not that easy. You can't simply replace the machine learning method, the model, and expect that everything works better. It might even look like it's working better in your evaluation, but you really then have to check if it's also working better for independent data for novel compounds, which the system has never seen and which are totally different from anything it has seen so far. So we are now at the point that we can look at the results. What are the results? Now we are training machine learning models here, so we have to be careful about one thing, and that is we don't want to know if the machine learning method, if the model can memorize things. We want it to learn something. Again, we are going after novel compounds that the machine learning method hasn't seen before. So what machine learning has come up with as a field is cross-validation, okay? Where you use parts of your training data to validate the model, but you train the model only on other data. So it has never seen the data it is validated on. And for that, you split your training data into folds. It's 5 folds here. Then you train in one run your machine learning with these 4 folds, and you evaluate it on this fold. So it has never seen that, so it's all new data. It cannot memorize, it has to learn something. You restart, erase everything. This time you train your model here, 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 and here, and you validate on this fold. Again, it has never seen that. You repeat that for every fold. Then you have, in this case, 5-fold cross-validation. That's the nice point, you validate your model with every sample from the training data exactly once, so you don't leave something out. You don't give different weights to different examples from your training data. And that gives you pretty robust statistics of how good your model is. So let's use cross-validation, and we are all good. So we sort the mass spectra in the training set in 10 folds. We do the cross-validation that I just described, and we get results. And this is what we can also expect for novel compounds, right? No. Unfortunately, we often have mass spectra from the same compound again and again, measured on different instruments by different people. But the whole idea of spectral library research is that these spectra will be very, very similar. And now what the machine learning model does, it's not stupid. It will memorize these spectra. And if the same spectra come around, it will simply say, oh, I already know this one. Hooray, found it. That's the solution. We don't want that, right? So let's make a second try. This time, we again do cross-validation, but this time we make sure that no compound is found in 2 folds. So whenever we validate on one fold, it's not contained in the training data set in the other folds. That's working now, right? No, because we know that stereoisomers fragment highly similarly, and we evaluate in the end only on the 2D structure. So we would still get a machine learning model that is memorizing. I mean, it will be memorizing anyways, and that's good, but in our evaluation, we will get again inflated results. We will see annotation rates which we won't observe in practice. We have to be even more careful. And now the third try is structure disjoint evaluation, and there we make sure that no structure, no conformation is found in 2 folds. So all the spectra from the same structure are now in 1 fold. The machine learning model trains on the other fold, so it has never seen the structure before. Then we evaluate on that. And that is now pretty close, or the closest we can get when we evaluate on our training data. And unfortunately, there are many papers out here that don't do that, that actually do this. So cross-validation on the mass spectra, or if they are a little bit more careful, they do a cross-validation on the compound level. And in both cases, you get inflated annotation rates, which you won't observe in practice. And this is again not a theoretical problem. I have shown you these plots before. This time it tells you how often we annotate the correct structure, on the first rank of our output list. So these are the absolutely correct identifications or annotations of 2D structures. But then we also report how often we got the correct answer in the top 2, in the top 3, and so on and so on. And Google, you would look at the first 10 results, for example. So if it's somewhere in the top 10, everything is fine. And this is CSI FingerID back then from the PNAS paper in performance. And one time we really did a cross-validation on structure. So structure, disjoint, cross-validation. And one time we only did a cross-validation on the measurements. So only the MSMs were sorted into different folds. And you see that the difference in performance is massive. That's almost 20, or no, it's more than 20, no, it's a little less than 20 percentage points, okay? So if you see somebody evaluate their method without this structure disjoint evaluation, I don't know how good it will perform in reality, That really depends now on how often different measurements from the same structure are present in the data set. But I can tell you one thing, you shouldn't trust it anymore. So this is now the complete good practice for the evaluation of in silico methods. All results that I'm going to show you follow these ideas and paradigms. And again, this should not be something that people discuss, but this is more or less the minimum standards that you have to follow. And again, the problem is that not all papers consider all of these points. So I already told you about the structure disjoint evaluation and why this is super important and why otherwise you get inflated results. I mean, it's in some way realistic because the tools will also see data from compounds where they already have seen a tandem MS, and then if they perform better, that's very good. But the point is then you could also do a spectral library search before you start your in silico methods. That with this is it's all novel compounds. Second point, don't search in a tiny database for evaluation. In many cases, you'll only get one candidate back. So what does it tell you that then your method ranks this one candidate at the top position? Not so much, okay? So search in a reasonable database like PubChem or ChemSpider. This is not what you would search in practice, but for evaluation, it should be definitely the thing to do. I told you that it's good to report statistics for all relevant ranks. Yeah, we have also seen papers where they only report the top 5 or only the top 3 or something. Why? What's so special about the top 3? I mean, with these plots, you can pretty much show all the ranks, and it's just more information, and it always looks a little bit fishy if people just report one particular rank. Why that rank? What's super important is evaluation on independent data. We made cross-validation, and we hope that this is also what we can expect from independent data, but in reality it's not. As far as we know, the performance of all methods always drops, at least if they use machine learning, it always drops on independent data. And the problem there is not so much that the data is really different or measured different or something like that. The cross-validation data is also pretty heterozygous, so very different compounds in there, but nevertheless, the compounds form little clusters, so you often have a similar compound in the training data, even though you made this structure disjoint evaluation. And you don't have that then often for these independent data compounds. And as I said, or I don't know if I mentioned that, metascores. Metascores are something very special. By the way, they also use machine learning, so they have to be evaluated using structure disjoint evaluations. Since they, in the end, only come up with 1 or 2 parameters, people often don't do that. That's a little bit, it's not perfect, but it's also not that bad because it's only 1 parameter. I have to say that I personally don't like metascores, and I'll make a separate talk about that. Why? But for this talk, the important take-home message is that it really doesn't make much sense to evaluate a metascore and believe that those evaluation results have anything to do with reality. That is not true. Okay, this is just totally overestimating the power of these methods. One thing that I found that people confuse a little bit is they hear metascore and they think metadata, but be warned, metascores, at least the one that I'm talking about here, have nothing to do with metadata, okay? So metadata is cool, metadata is good. We use metadata, you use metadata as soon as you enter ppm, mass accuracy, yeah? But metascores is not good. I mean, it's like bringing a sledgehammer to a lock-picking contest, okay? It might, result in you opening the door faster than anybody else, but what exactly is that going to tell you? Now, doing a good evaluation is really important, and actually papers have been written about that because we often see other papers where it's not been done in this way. And as I said, in the fields of bioinformatics and machine learning, this is not something that you even discuss, okay? people from machine learning or bioinformatics might not be aware of that, but everything else is clear. Okay, that's how you do it. But sometimes on the chemical side, we see papers where we were really not happy with it. And this is not like me saying NMR wrongly. Okay, this is not something where we can say, oh, yeah, not perfect, but who cares? This is really the minimum standards that we should adhere to. And by the way, some of this is written already in here. Okay, and this is also a paper worth reading. It's more from protein research, so proteomics, but the point is their rules also apply to us, like evaluating against other people's method. We have seen papers being published where for exactly this same task, there are already 10 or 12 methods out there, and they publish a method and it's not evaluated against a single other method or against 2 or 3 randomly picked method. How is that even possible? How did that go through? Okay, I'm getting a little bit upset here, so I better stop. So good evaluation is super important, otherwise you can forget the results of the paper. And the funny thing is, this is not me who is saying that. I mean, in 2015, we had 2 papers or several papers which did good evaluations even before that, like always searching in large databases and stuff like that. This is from the paper by Felicity Allen and Greinert and Wishart, where they also report, for example, very similar plots that I just showed you. Yeah, okay, they report the number of correct identifications on rank 1, 2, 5, 10, and 20. So it's a little bit more compressed and it is not that full, but in principle, this is exactly the same plot that I just showed you. And that's again from 2015, and those 2 papers were written completely independently. So these are the standards of the fields, and I think all future papers should adhere to them. Okay, so if they don't, be very careful. And finally, we come to the results. To the results slide. So back in the PNAS paper from 2015, we did this evaluation and we also evaluated all other methods. And then we only added on top the new CSI FingerID version here from the Nature Methods 2019 paper that has a little bit more training data. It has more kernels. It has more, I don't know. It's a little bit smarter than the original one, but in principle, it is still the good old FingerID, CSI FingerID. Sorry. By the way, I never told you what the name really means. It has a meaning, but it's, yeah, the abbreviation is better than the meaning, okay? Anyways, so what we already saw in the PNAS paper is that in comparison to the other methods out there, and I would doubt that we have a single method out there now which performs substantially better than CFMID, which is newer than CFMID. We saw that in comparison to all of these other methods, we got 2.5-fold more correct identifications at the top 1 position. So correctly placed at the top position. Again, this is the top positions up to the top 20. So that's really dramatic. Also, in comparison to the direct predecessor FingerID, which, as I told you, is just not having this part of multiple kernel learning. So that is a dramatic increase in identification performance, and it gets even better with this new version, which gives you then another 8.6 percentage points. And this is so dramatic, and we have now been fighting after we've gotten to this point that we got 2.5-fold more annotations. We thought, okay, this will continue like this, and we will soon pass the 50%, but this never happened. It's really, as in often with machine learning, you have one great idea, multiple kernel learning in this case, and it really transforms everything, but then you fight really hard for every single percentage point, okay? And I have no idea how far we can get here. I mean, we are searching here in PubChem, which is not what you would do in practice, but nevertheless, our hope were that at some stage we would pass 50 or 60%. I don't even know if that will happen. I mean, there are so many, let's face it, crappy spectra, and crappy spectra doesn't mean they are measured in a crappy way. It just means they contain practically no information. Yeah, 1 or 2 fragment peaks. And then you have 10,000 candidates in PubChem for this, say, I mean, all methods here got the same set of candidates, which were filtered by the molecular formula. We assume that we know that. See the previous talk, why. But anyway, sometimes you get 10,000 candidates, and then with 2 or 3 peaks, you have to decide which of these 10,000 candidates is the correct one. And always remember, if a spectral library would be as large as PubChem, the results would be much worse than anything that I'm presenting here. I'm absolutely sure about that. Okay? But even more convincing than these evaluations which we did ourselves is maybe blind challenges. I mean, the idea of blind challenges is that you get to see data, you don't know the solution, you submit your solution, and only after that you are told whether you were right or wrong, weeks after that. And maybe the best known such blind challenges are critical assessment of structure prediction, the CASP challenges. They have been run now for many, many years, 26 years. That's when they started off. The field is super interested in them. There are literally hundreds of people who are participating. It's a huge effort which goes into that. What is very important there is, this is so important that people which, I mean, this is about structure of proteins, and people who have a new structure of a new protein just resolved often don't publish that directly, but give it to the CASP challenges. And then the CASP challenges can hand those out to the participants. And so the participants always see completely novel proteins, which nobody really knows except for the few people who have recently solved them, okay? And then they can work on them, and we are absolutely sure that this is the performance that you will also see in practice, okay? So that's one thing, and it shows how important they take that as a field. I mean, experimentalists, people who are doing the X-rays, they have to provide those structures, and they think this is so important that they hold back the resolved structures instead of just publishing them or hiding them in some database so they can publish something later, because only they know the structure now and nobody else knows. Okay? The other important thing of these challenges is that there are many, many categories, and they change every year. But a few categories stand out, and everybody's absolutely sure that ab initio modeling, which is, I give you the sequence of a protein and you predict the correct structure, ta-da, can you please do that for me? That this is the most important category. Okay, if you could solve that, everything else is no longer needed. So that's the gold standard. Okay. You might have heard about these challenges recently because, yeah, they are somehow solved. Okay, and that's AlphaFold 2. It comes from DeepMind, the company by Google, which now participated for the second time. And the important thing here is that after many years where they measure the difference between what you give them as a solution and the actual true structure of the protein. And this should go up at some stage to 100%, but even different experiments will not give you a score of 100% if you compare the structures. So everything above 90 is considered almost as good as experimental data. Okay, and this is the score that the best contestant achieved on average over all these molecules, over all these proteins where they had to provide a structure. And what you see here is that for many years it didn't change that much. Okay, it went up and down between 30 and 40%, and before that it wasn't better either. That's one thing that I want to tell you here. Okay, the field didn't stop these challenges immediately, because obviously nothing is happening anymore. That's so not true. And during these challenges, also people had great ideas and they tried something out and they got a completely new approach. And then, yeah, they got pretty much with this new approach the same results that people got before that with a completely different approach. And that was interesting. Yeah. And then at some stage, DeepMind got interested. And I think they got interested because these challenges were, other point, for 26 years, and the field is still interested and still thinks they are serious, and it takes them serious, okay? And DeepMind is a huge company with people from machine learning who know 1 million times more about machine learning than I do, probably, just a rough estimate, okay? And they also earn more money than I do, and they earn more money than, I don't know, a lot of people. They are really good, and machine learning experts are currently the most expensive experts you can probably buy from any experts. Maybe something like that, at least from the mint mathematics and natural technology, blah blah blah. So this huge company with 10,000 employees wouldn't dive into this challenge if they thought, yeah, maybe 2 or 3 people are interested and maybe not, and they are not really sure if this is important. They say this is important, but then they don't really make these challenges every 2 years. They just went away. Yeah. Also important is DeepMind didn't, simply decide that they wanted to do machine learning one day and then 2 days later, they revolutionized these CASP challenges. They already worked on machine learning methods for different problems for many, many years, okay? The last thing is, they weren't interested in the first 12 challenges. Why were they interested in the 13th? As I said, probably because, there were 12 other challenges. But the other point is, there were solutions during these other 12 challenges, loads and loads of great ideas how you could actually solve that. And they were standing on the shoulder of giants. I mean, they didn't start from scratch. They might tell you that because it's cooler if you want to sell a paper. I would do that too. But in reality, they had all these other methods, all these ideas flying around. And that is really, really helpful if you want to build a new method that then revolutionizes everything. And they did. Okay, they are close to 90. This is a game changer. This is everything. You can, if this turns out to be true in other evaluations as well, I mean, we have to wait for that, but it really, really looks like this is a transforming thing, okay? You don't have to do the experiments anymore, which allows you to suddenly screen millions and millions of, I don't know, self-generated proteins for special things, or you can test all the proteins that you know so far, if they, whatever. I'm not an expert there, but it really opens up new venues. Now, we also have our blind challenges, our blind competitions. And those are the CASMI challenges, critical assessment of small molecule identifications. They were started back in the first challenge, I think, by Steffen Neumann and some people. Then Emma Szymanski came to help him. And since then, they are more or less the people in the back who are running these challenges. And we have to be very, very, very thankful to Emma and Steffen that they are doing it again and again. And I don't think the field is, paying enough attention to that and praising them enough for what they are doing. Yeah. In principle, the challenges, just to make that short, are exactly the idea that which I told you. Blind challenges, you download data, you upload your results, and then you get an evaluation. One problem with the CASMI 2016 challenge, which was not the last one, the one before that, was that never really a winner was declared, or let's say a winner was declared, but the metric was so funny that nobody really was then interested. Okay, so that's why I'm showing you a little bit more in detail what the results are. This is searching in ChemSpider, so that makes sense. Not searching in tiny database where it's luck if you get the correct identification or not, and you can forget what results the method actually gets. I'm also showing you just the results of one category 2 here, which is actually the category that I think this is all about, that in silico methods are about. But there were other methods which allowed you to use meta scores. Yeah, okay. And even other categories, which I'm not totally sure. Yeah, it was a little bit of mixture. That was a little bit unfortunate. But nevertheless, here are the results. And here's CSI FingerID. Oh no, here's also CSI FingerID. How is that possible? Because there's a second version of CSI FingerID, which uses the setup of the multiple kernel learning, which I told you is the most important change in CSI FingerID. The rest is in comparison, relatively small. And they replaced, and with they, I also mean me. Okay, the authors replaced, but I'm not a machine learning expert, the machine learning setup, which for the regular standard boring CSI FingerID is just a batch of support vector machines. They replaced that by something new and exciting in the field of machine learning, which is input-output kernel regression. I'm not going to talk about the details. Please look into the paper. It's not that easy to read for somebody who's not from machine learning. But what you see is pretty often that CSI FingerID and CSI FingerID IOKR perform very similarly. The differences are not that big. Okay. Anyways, what we see here is, yeah, these two tools have the most correct identifications in the top positions and so on. Here, it's a little bit worse than CFMID. Yeah, but it's looking good, right? But this is not the complete truth, because what we had in CASMI 2016 was we had some challenges with positive iron mode data and some challenges with negative iron mode data. So what always helps if you look a little bit more closely and do the statistics for such important differences individually. And it really helps here. Because if you look at the two categories individually, okay, we see that, wow, now the differences are getting bigger here, okay? And we now have more than 2 times the number of correct identifications of CFMID. Now that's cool, yeah? And the IOKR version is performing a little bit worse. But how is it possible that, oh my God, we got 0, 0, and 0 here? How is that even possible? Now the point is that Kai Dürkop back then thought we don't have any training data in negative iron mode, so let's not even try to train a machine learning model with positive iron mode data and then apply it to negative iron mode data, because it makes no sense. Let's wait until enough negative iron mode data is available. But somehow nobody else thought this was a good idea. And yeah, I mean, the other tools like Magma, they also work for this negative iron mode data. They don't have to train anything. So yeah, we were the only ones. CFMID was also applied to the negative iron mode data. We were the only ones who thought this was a good idea, and everybody else participated. And yeah, the identification rates or annotation rates are in comparison not that good, but you could collect a few top hits here. Every method collected a few top hits here. And so in total, yeah, everybody was a little bit better, except for CSI FingerID. But if you look only at this thing, I think this is what you now would also see for negative iron mode data. Or I don't only think that, I can prove that. Because we redid the analysis, but I mean, one thing that is bad about blind competitions is that we can't make them structure disjoint. We might have the training data of exactly this structure already available, and then it looks like we are doing a wonderful job when in fact our machine learning method is only memorizing. By the way, CFMID doesn't have that problem that much. It's not overfitting. This is pretty much known, so it doesn't matter for them. So it's working like those other numbers which you can also expect in practice. Anyways, I took out these two and I replaced them now by the newer version of CSI FingerID, which was published in 2009 with the Sirius paper. And what you see is you have really a drop in top identification. So correct identification is the top position. I don't know this number, it wasn't in the paper, so I thought I leave that out. It's not that important. But we now see that we have negative training data. We also identify a lot of compounds for negative ion mode data. And again, we are almost twice as good as CFMID. Yeah? And in total, we even have more correct identifications now, although we are doing the structure disjoint evaluation, which corresponds to all novel compounds, as I like to say. What we use as the default here is a combination of everything that we could find. And that contains about 500,000 structure, now going up to 1 million structure maybe. And it's all the structures from these other databases. And if you search the CASMI 2016 data in there, you get almost 3 out of 4 correct. Okay? And almost 85% in the top 3. And this is again ensuring structure disjoint evaluation, all compounds are novel. And once again, you might say, but spectral library search gives me better results. I doubt that, because those were also many compounds in there where no spectra were available in the wild. So it couldn't have found those because they were not in any spectral library. I don't know how many, like 2 out of 3 or something like that. So you would have completely missed them. So spectral library would have annotated, I don't know, 25% correct. And also when the spectral libraries get bigger, even as large as this combination of all the biomolecular structure databases, it will perform much, much worse than it's currently. Currently, it's simply so good because we have so few candidates. So this was not the last challenge. There was another challenge in 2017 where we officially won 3 out of 4 correct categories. We were then declared best automated candidate ranking method, and we got 6-fold more correct annotations than the runner-up, where I have to say, again, CSI FingerID and CSI FingerID IOKR are different flavors of the same idea. But the next non-CSI FingerID method, we got 6-fold the time correct annotations. But then none of the other major tools participated. So, and there was so many issues with the data. It was MSE data, but many contestants didn't know that. And then they told us it's MSE data, but I'm not sure that all the contestants even knew what MSE data was, because it's really, really special to see those isotope peaks. In particular, since they removed the isotope peaks of the precursors. So spectra were niceified, and it was really, really hard to make any sense out of that. And we were lucky because we had thought about the problem of fragmentation spectra with isotope peaks 1 or 2 years earlier, and we had already something working, which we didn't really know if it was working because we had no data to evaluate it. And this was the first data where we could really evaluate it on. And yes, it worked. Hooray. But I would say treat those results with care. The 2016 was the last challenge where we really had a competition among methods that's worth looking into. And now the sad truth, that was the last CASMI challenge. And I don't want to complain here too much, like, oh, we want another challenge so we can show how good we are and blah, blah, blah. But this sends a signal. I don't know if I was Google, DeepMind, whatever, and the field is saying that this and this challenge is so important for mankind and the field and everybody, and then there are no more challenges, I would say it's not really important. I would never enter such a field. And this is something that I currently see, that people from machine learning, it's super hard to get into this field anyways, because it's really, really complicated to get all those chemical details right. Proteomics is much nicer in this respect. You just have strings, yeah? And then you have this very, very complicated field, and the field itself is not really sure if this is important or not. Yeah, a little bit important, but not important enough so that I would do anything, or that I would pay kudos, pay respect to the people who are running these challenges. Yeah. I'm not DeepMind, but if I was, I wouldn't touch this. So I would really think we need these challenges again to tell the rest of the world that we really believe this is important, that you really believe this is important. I mean, I as a developer, I am also one of those guys. I can also move to cancer research. I don't know. I don't give up that easily. So even if people tell me again and again that what I'm doing is not what they're looking for, I still keep on working. But I think already a lot of people have lost interest and left the field for good. And this is very sad. They won't come back. Okay? So this is more or less it. But before we stop, a few thoughts on spectral quality, because I think this is important if you want to use our tools at their peak performance. So the point here is that, or the most important point is, no peaks, no information, no performance. Okay? Bad data in, bad results out. Okay? We can't do black magic. It sometimes looks like we can do black magic. We've seen evaluations where people put in an empty spectrum and just by chance, CSI FingerID returned the correct answer. But that is more or less just by chance. I mean, there might be a little bit of thinking about it. Like, yeah, this structure should produce these peaks and this structure should produce these peaks. And so this is the most reasonable structure because it didn't produce any peaks. But if your candidate lists get large, there will be many candidates that don't produce any peaks. So don't expect magic if you have no information, no peaks in your spectrum. We can't do anything for you. Second point is, there has been this rumor that peaks with high mass are more informative than peaks with low mass, which comes from the GCMS field, EI. But they do not have precursor filtering, okay? They don't do tandem mass spectrometry. And for them, indeed, a peak at a low mass is something that you see in many, many library spectra, whereas those at higher mass are rarer and so more informative. But for us, this is not true. If you see a fragment peak, which corresponds to an H2O loss, this is super uninformative for us, okay? Almost every molecular structure could produce such an H2O loss. So don't change your instrument settings so that peaks at particular masses are measured more often. I already talked about MSE. Okay, please tell the methods and make sure that the methods can actually handle that. Okay, don't throw data a method was not built for at a method and then complain that it's not working. Oh, we evaluated it on, I don't know, cat pictures and it cannot identify cat pictures. What the heck? Okay, that's not fair. And I don't mean our methods. I've seen that with many methods. Many in silico methods were developed by other people, and then they're evaluated for something they are not at all made for, and then people complain that they can't do that. Hello? Anyways, tell the method what data you actually want to put in. Last point, or second last point, chimeric spectra are often still okay for spectral library search. Okay, you see 10% noise peaks, which are not noise peaks. Yeah, they correspond to a compound B, which is measured together with a predominant compound A. Yeah. For in silico methods, chimeric spectra are really, really bad. They are really a big problem. Okay, just be careful with chimeric spectra. Test for chimeric spectra, and don't be too depressed if it didn't work that well. And then one thing, I mean, we'll publish something soon about what fragmentation, what collision energies are the best for CSI FingerID, but what we usually see for all in silico methods is that ramp and pseudo-ramp spectra are better because they give more peaks, and more peaks is more information, and more information means better annotation rates. One very last point. which is a lot of papers are nowadays published, and then many actually evaluate against other methods, and evaluating against CSI FingerID is not that easy. So I thought I say a word about that. Why is it not easy? Because CSI FingerID is actually run as a web server on our side. You don't see it. Your computer, if you run Sirius, just submits something in the background onto our web server, and this then puts it onto a compute cluster with a job. I mean, there's a lot of databases, there's loads and loads of things going on. So that was a really, really good design decision to do it this way. Okay, otherwise the installation of Sirius on CSI would probably take, I don't know, 2 weeks, and can only be performed by people who hold a PhD in computer science. The nice side effect for us of this nice design decision is that we can monitor how many people use our service. We don't record anything, we just look, how's that, geohashing or something? So which city does the query come from? Which country does the query come from? How many queries come in? Okay, so we are approaching 100 million here. But this is not about patting our back and saying how great we are. This slide is about this last point. This whole setup makes it really hard to evaluate against CSI FingerID in a fair setting, because as I said, you have to do it structure disjoint. So what you can either do is take results from a previously published data set and simply compare against them. Or if you really, really have to do it with a new data set, simply contact us. We can set up something so that you get a structure disjoint evaluation. And you won't believe it, we are not going to lie. We are going to be super fair and do it exactly in the way that you get a fair evaluation. Okay? So, as I said in the previous talk already, you can simply try it out. Download our software and play around with it a little bit. It now has a very nice option to actually directly read in MZML files, which makes it relatively easy. If you want to know how to get the MZML data into Sirius, just look at a different video tutorial that explains that to you. Yeah. With that, I come to the conclusion, which is pretty short because I said everything, so I'm not going to say that again. But I again want to highlight some people that contributed. I mean, most importantly, it's Kai Dürkop for CSI FingerID, who is the main brain, the main machine learning brain behind it. Our cooperation partners, we would have never approached this questions in the field of machine learning without experts from machine learning, I have to say. I'm always a little bit shocked that people simply apply machine learning methods. I don't know. They have never done anything in computer science, never anything in machine learning, and they know how to do machine learning. I didn't know how to do machine learning when we started that. So I did it together with the experts. And the experts are back then all from Aalto University in Helsinki, Juho Russo, Huibin Chen, and Céline Bouard, who is responsible for the IOKR variant, input-output kernel regression. The new scoring is Marco's work, and if you are happy with the software, you can actually send this guy, pay this guy a beer or something, because Marcos really makes our software nice, shiny, and fixes all those nasty bugs, which make it a horror to use. But again, you can't really publish something for fixing a bug, right? So thanks to all of them. But before I stop, I wanted to mention one last thing, closing remarks, and that is we need data. Machine learning methods need data. We now have this data, but there are many, many other groups who might enter the field, but they don't if we don't provide them the data in a nice and shiny way so that they can dive into the problem and not have to care too much to have year about, I mean, be honest, these machine learning people, okay, they can publish papers which are then cited after 5 years. They get, I don't know, 25,000 citations. It's not like we are the coolest dudes out there and can tell them, yeah, think about my problem, think about my problem. This is not really true. So I'm super happy that some people have started to overcome the tragedy of the commons. Okay, which is everybody thinks it's super important to have this data out there, not only for training machine learning methods, but also for spectral library search. But then uploading this data, you don't really get any gratifications for that. You don't get any kudos. You don't get a publication out of it. And I understand that. But this is the same as we are fixing bugs, as I said. We are fixing bugs and nobody pays much attention. You think this is done in the background as well. But I understand that this is not easy. Many things to those people who cared, who started to care many years ago when nobody else cared. So these are the people that make it possible that actually CSI FingerID exists and all other methods that use machine learning methods exist. And I really hope that more kudos are given to them for providing the data, and B, that other people also contributed their data publicly. It should be publicly, okay? There are possibilities now for us, for example, if you don't want to upload your data to a public database, you can give it to us and we can train CSI FingerID on using it, and there is no need to publish that. But then again, nobody else can use it. And as I said, I want other people from machine learning to enter the field. And how is that going to happen if there are so many secret data stores here and there? So become our next hero and release your 10K spectra to the wild, please. And with that, I now really come to an end, and I thank you for your attention. Bye.